Start recording. Okay, here we go. All right, so we are going to do a little review, and we're going to start off with a function, a very simple one, x cubed. We find first derivative, we set it equal to 0, and we solve, and we got a possible critical point. We don't know what kind of critical point it is, but we know it's a critical point. And the step we would do is we'd stick it on a number line, and we would test, bless you, just to the left and just to the right. All right, so if I take -1, so I'm going to do f prime of -1, and I get a positive answer. So that means I'm increasing on that interval. And then I'm going to pick another number over here, f prime of +1, and we'll see, whoops, we know that that's greater than 0. If I put it in here, I also get a positive number. So that tells me it's increasing everywhere. Okay?
Exponential.
No, don't worry about exponential. It just goes, it increases everywhere. Okay? So, but does that tell me is 0 an extrema? No. The only way it's going to be an extrema is if it changes signs. Either positive to negative or negative to positive. That means if I'm positive, that means I'm increasing. If I was negative, that would be decreasing. Okay? So mins and maxes, are basically positive to negative or negative to positive. Okay? All right? But in this case, it's neither. All right? So now what we're going to learn, we're going to take this a step further. We're going to actually now find this second derivative. And this second derivative is going to be 6x. All right, what does second derivative tell us?
Acceleration.
Yes, and if you're dealing with movement and moving bodies and stuff, definitely. But in for our purposes here, second derivative talks about concavity. Concavity. What do you mean concavity? Basically where the function is increasing, where the function is what I call hold water or concave up or concave down. That's okay. Sorry, no worries. All right, well, let's analyze this and see what happens. So you do the same process. You take second derivative, set it equal to 0, and I did not check that homework. We're going to go over it more, but yeah, I'm going to stack it. And we get another critical point, x equals 0. They're the same. In fact, sometimes you will solve second derivative and get the exact same one of the critical points that's up in the first one. Now, we're going to do another test. We're going to test for concavity. And that's what second derivative is going to do. This chart here was f prime. This one's going to be f double prime. Now here we go. What you're going to do is you're going to test values again in the interval. So I'm going to test a value left of 0. I'll try -1. So f double prime of -1. If I plug it in the second derivative, I get a negative number. What negative means is it's going to be concave down. And then if I pick a number to the right of 0, I'll pick +1. 6 times 1 is a positive number. It's greater than 0. So it's concave. Concave up. Okay, yeah.
So basically what that equation is doing is just keep on increasing, which is basically the graph
of x cubed. Remember, all this information, guys, is talking about the original function x cubed. That's what we're describing. What you're going to have to do, and I'm going to create some little sample charts here, is that you're going to take this chart and this chart and piece together what this graph is what it's doing. So if the only critical point I have everywhere is 0. And what it's telling me is, guys, is it's increasing everywhere, but it's changing from what I call spill water to hold water at 0. This is what it looks like. Okay? So think of it. It's increasing everywhere. Bless you. Bless you again. But at 0, see how I'm concave down? I'm negative here. And then at 0, I switch to concave up. So in all, second derivative talks about concavity. Now you would think we're done and like, okay, homework. No, we have a lot to talk about still. And so I want you to really focus. But I kind of alluded to this concept of what second derivative does. But we're gonna use it more. And second derivative, by the way, also tells us more information. Okay? Is everyone okay what second derivative does? We call this point here a point of inflection. All right? Sometimes I call it, find your POIs. 0. And a point of inflection is where concavity changes. Again, a point of inflection is where the concavity changes. Yeah.
What's like the mathematical definition of concavity?
It's basically right here. If double prime, if the second derivative of a test point is negative, then it's down, concave down. Concavity is basically the curvature of the graph. All right, here's some examples, guys. If I was going to look at, this is concave up. All right, this is even concave up. I know it's kind of slanted, really, but what happens is you kind of got to look at that it just will change, okay?
Is there concavity on a parabola?
Yes, let's look at a parabola. There's a min, and it's concave up everywhere. Okay? So, I mean, hey, here's x squared. 2x is first derivative. 2 is second derivative. Do you see how the second derivative is positive everywhere? That means it's concave up everywhere. Negative x squared would be negative 2x. And negative 2. That means it's concave down everywhere. The negative. Okay? And this tells me at 0, and anything left of 0, I've got a increasing because I've got positive slopes. And anything to the right of 0, I'd have a negative slope. Okay?
Question, what
yes.
Means, the second derivative?
Well, the second derivative just turns into a constant. So there's nothing to plug in. So it's constantly negative everywhere. And if you look,
It doesn't matter if it's 2, if it's 4, if it's
you care about the sign. Because it's negative, and it's always going to stay negative 2 no matter what, that's why it's concave down everywhere. Okay? X cubed, however, I don't even need that. So this has no point of inflection, the two parabolas, but x cubed has a point of inflection. When I set the second derivative equal to 0, I get x equals 0. Everything to the left of 0, I've got negative, concave down. Everything to right of 0, I've got concave up. Are we all right?
Wait, so the more, let's say, the more power the x has,
let's not get into patterns yet. We're going to look at this. I want to just drive home definitions right now. I know you're trying to find a pattern and stuff. There really isn't, because remember, there's natural logs, trig functions, there's a mixture of them all. And sometimes, guys, you're going to have 3 and 4 maxes and mins and 2 or 3 point of inflections. I mean, you can get some really crazy things going on. Okay, and we're gonna find one of those later on today. Okay, all right. Now, some more observations. Yeah.
This is just a refreshing question.
Yes.
So when you first find your critical points
From first derivative. Yep.
from the first derivative.
Yep.
You said equal to 0. You plug it back into the original to get the pair.
To get the actual ordered pair,
Yeah.
correct.
That's from the first lesson.
Yes. Yes. I mean, we were going back way back. We were looking at, max and mins on a closed interval. We would test endpoints. We're looking for the biggest y and the least y, okay? But we're kind of getting back into theory right now. All right, I need to talk about some theory here, and I want you to understand some things. Understand, let's take x cubed again. What I want you to do is look at this from a graphical point of view. You know what? I think I have it stored here. No. Okay. All right, let's do this. This is easier to do it this way. So I'm going to put in 3 graphs here. We're going to put in x cubed 3x squared and 6x. All right, let's look at all these graphs together and let's try to interpret how they relate to each other. So remember, the black one is my original. That's the one I'm really talking about. The red and the blue give me information about black, okay? So let's look at the black here. Look at the red graph. The red graph is my first derivative. Notice that the red graph is decreasing everywhere left of 0. Wherever first derivative is decreasing, I'm concave down on my original. That's one observation. All right? And the reason is this is a very popular AP exam question. They won't give you the function. They won't even give you values. They're going to give you graphs. In fact, they may not even give you the black one. They're going to give you that. And they're going to say the red one is y prime and the blue one's y double prime. Can you tell me what's going on with the original function based on that information? All right, let's try to do that. Two things about increasing, decreasing. Let's handle the increasing, decreasing. Notice the red graph is my y prime. Do you see that y prime is positive everywhere? What's the y value here? What's the y value everywhere on the red?
Positive.
It's all positive. What does that tell you about the original?
It's just going up.
It's increasing everywhere. Remember, first derivative talks about increasing, decreasing nature. Now, forget second derivative. I'm just all basing this off. Notice now, when we talk about concavity, notice that the red graph is decreasing here. Wherever it's decreasing, that's where my original one is concave down. Think of the second derivative, guys, as really the first derivative of the first derivative. Right?
Yeah.
All right? So I've got negative slopes there. That means what's really talking about is the concavity. Another way to look at this, look at the blue line. The blue line is my truly my second derivative. Do you see how it's negative everywhere? So if it's negative, that means it's concave down everywhere here. Right? And see how the blue line is positive here? That means it's concave up everywhere there. Again, I'm talking about the black graph, the original. Okay? And again, notice how my red graph is increasing everywhere. That means I'm concave up. And also, again, remember, the red graph is positive everywhere. That's why I'm increasing everywhere. We're going to do a lot more of these, guys. I'm just trying to get this stuff that, makes the brain actually struggle.
Let's say they give us this 3 graphs, and they ask us the next.
They're not going to give you the original. They won't give you the black.
No, I know.
In fact, they may just give you the derivative.
I mean, let's say that the black one is the first derivative, then the red one is the second, then the third.
Since we know all the answers, let's do one from scratch. Let me put in one here. Sophie, you had a question?
Yeah, so couldn't we just do that based on one of the graphs, or do we need both?
Yes. No, you can literally take the first derivative graph and find out concavity and increasing, decreasing from it. Yep, and that's what we're going to do right now here in a minute. All right, The what?
The third graph.
The third graph is the blue one. That's the second derivative. Notice it's negative. So there's 2 ways to identify concavity.
That was a stupid question.
Yeah.
I forgot that the first one was the original.
Right. No, that's okay. Everyone does that. All right, let me give you a good one here. All right, I'm just going to put in just the first derivative. I'm not going to give you the original. I'm not even going to give you the second derivative. All right, let me find the first derivative here. All right, here we go. Again, it's easier to type these in. All right, let's see if we can derive some information here. Now this one's going to have some asymptotes. Let me find another one. Hold on.
One of those big gulps, I feel like you just caught.
All right, let's look at this here. F prime is. All right, let's see if this works here. Negative x times e to the negative x squared
That's just like a bad.
divided
Yeah,
by.
no, it's like his soul go bad. Like he just drinks a nice.
He's just
he
so
must be
tolerant.
Yeah, like he's like totally.
Yeah, he's so
yeah.
tolerant that drinking a little bit more.
Are you like
He's so
that too?
tall. What?
Are you like that as well? Do you drink alcohol?
I mean, yeah, I drink a lot of coffee. I don't drink coffee before I go to bed. I'm not gonna say, but I do like. I like drinking a lot of coffee. Just 'cause it's good.
My
I
Mis-
never sleep.
the other Mr. Danley, my son, he's a coffee nut. He
Drink
literally.
coffee?
I drink coffee, but
I think everything.
I like coffee at night. I don't know why. Yeah, I'm not a morning coffee drinker. If I do morning, I do an iced coffee.
I'm like a 24/7 coffee drinker. I can drink it all the time.
Well, Chris used to work at Starbucks for years,
Oh.
and he became really. So he did a French press. He really get into all that stuff.
They're so much better than like Keurig's.
Yeah. All right, guys, here we go. This is the first derivative. This is not the original function. All right. So let's see if we can talk about it. What's that? Oh, thank you. All right, let's talk about it now. All right. Do you see how it's increasing from here to here? If it's increasing, what does that tell you about the concavity?
It's increased. It's
No.
up, concave.
It's up.
It's concave up. Okay. So let's see if I can piece this. All right. We're gonna kind of. All right. Let's see if I can do this here. Ah! I cannot believe I did that. Undo. Yes, thank you. All right, here we go. So we got our magic point right here. Okay, right here it's changing, increasing to decreasing. All right, remember, guys, this is first derivative. So since it's increasing, I'm just assuming that's -1. All right. Basically, I'm concave up. I'm only talking about concavity right now. Now I'm decreasing all the way down to +1. All right, if I'm decreasing, that's concave down. And now I'm increasing again. And so if I'm increasing, I'm concave up. Now let's talk about the increasing, decreasing nature of the function. Notice that everything up to 0 is positive. See how y? Do you see how y is positive everywhere here? That means what? If it's positive, it's increasing. This is the first derivative graph.
Now it's the
This green is still the first derivative always. I've not shown you the original. I'm not showing you the second derivative yet
How do we judge concavity on this?
because it's increasing. So here we go. I know it's hard to wrap our head around.
I thought you used the second derivative to find
You can
concavity.
do both. You can use first derivative and second
So why
derivative.
would you ever use the second derivative?
You'll see why. To find them. We're doing this graphically, but to analytically find the actual points of inflection, you have to find second derivative set it equal to 0.
Are you saying that it's increasing to 1?
My graph is increased. Again, this is f prime, guys. This is increasing all the way up to -1.
Okay.
When the first derivative is increasing, that tells me the graph's concave up, increasing up. Okay? Since it's decreasing everywhere, all the way to 1, that tells me it's concave down. And because it's increasing from 1 on up, then it's up. Now let's go talk about what just first derivative means, increasing, decreasing. I've handled concavity. Yes.
What is this? Sorry, what is this equation that?
We don't know.
No, but like,
This
Like the
is the
first
derivative of something.
okay,
Okay? Yeah, the derivative is -x
not right.
I told her it was x cubed.
e to the -x squared over 2. This is y prime.
Can I ask you something?
Yeah.
What we're doing right now, it's integrated, right?
No, we're going forward. We're not going backwards yet.
No, I know, like,
No, I mean,
Anti-derivative,
try, like,
right?
you give us the first derivative, and then we are trying to find the.
We're trying to analyze the graph. We're not actually trying to find the original function. Guys, we are not trying to find the original function.
But we could.
Not yet. We don't know any rules yet.
No, we're just.
All we're
find
trying to
the
do is basically curve sketch the original function.
Okay.
Okay, that's all I'm trying to do is curve sketch it. All right? And the derivatives, first and second derivative, give me information about that curves. All right? And if you think about what a curve, the only possibility of what curves do is they increase, decrease, and they hold water, spill water. You put them all together, you've got all the curves. Okay? All right, let's talk about here. Notice that first derivative is negative everywhere here. If it's negative, that means I'm decreasing. Let's see if we can take this information, guys, and somewhat curve sketch what our original function is. So we've got -1, 0, and 1. Those are some of my magical points or critical points. So everywhere to 0, I'm increasing. All right, so I'm doing that. And everywhere to the right of 0, I'm decreasing. Now I got to put my curves in. Okay? At -1, I'm concave up. Then between -1 and 1, I'm down the whole time. Okay? But up to 0, I'm increasing. Hold on. I'm increasing. All the way up to 0, I'm increasing everywhere up to 0. But between -1 and on either side of -1, I'm going concave up, and now I'm concave down. Up. Yep. It's like that. Now, on the right of 0, I'm decreasing. Okay? So now I'm going, and I'm still concave down. All the way up to 1. So I'm concave down, but now I'm decreasing. And as soon as I hit 1, I'm concave up, still decreasing.
Critical point.
Up. I should be joining this together better. Now I'm up. Okay? Increasing all the way to 0, decreasing everything to the right of 0. Right? That's what that does. I'm changing concavity at -1 and 1. Notice I'm hold water, spill water. I'm still spill water. Now I'm hold water. That is the graph of the original. And the equation of the original is e to the -x² over 2.
But that's what I'm saying, kind of like without knowing. I know we're not finding the equation, but we're kind of like integrating
Right.
the graph itself.
Right. Kinda. But you don't have to, we don't know how to find
The equation. That's it.
the equation yet. Yeah. But in a sense you are. Okay? All right, guys, we're going to do a lot more. We got a lot more of this stuff. So let me just type in real quick. This is going to be e to the -x² divided by 2. Okay? And so that black graph is our graph.
Can you scroll up? Like, not really.
What's that?
Can you scroll up a little bit?
Yes.
Oh wait, calculus is easy? Yes. With our new teacher, Miss Bailey. Before? No.
All right, so that makes sense, right, guys? This is I'm hold water here, but right at this point, you can see how it changes concavity, and you can see how the first derivative is increasing and then decreasing. Okay? All right, more practice here. Let's keep going here. What I'd like to do now is I'm going to give you some charts. No graphs, no functions, nothing. I'm just going to give you data, and I want you to be able to tell me what's going on here. All right, so all right, how about this one? I'm going to give you some intervals here, -infinity, and x lies between -2 to infinity. All right, and then we're going to do -2, 2, and then +2 to positive infinity. I'm going to do a test value. I'm going to pick a value in this range. I'm going to pick -3. Here I'll do x equals 0. Here I'll do x equals 3. I'm telling you this. F double prime of my test value is positive f double prime of 0 is negative, and then f double prime of that test value is positive. Guys, I'm going to give you something like this on the quiz, and you're going to have to tell me the concavity. On this interval right here, what's the concavity?
Positive?
Up. Perfect, because it's positive. This one is down, because it's negative. Because this is positive, it's up. Easy peasy, right? Okay, so we understand that when we're dealing with intervals, when we're dealing with second derivative describes the concavity. But wait, Mr. Danley, you just showed me a first derivative. How? Just understand that the first derivative can find a bunch of things, okay? And I'm trying to really lay this out succinctly as I can. So, f prime, what all does this thing tell me? Let's recap it. It talks about the increasing, decreasing nature of a function of f of x, okay, based on if f prime is positive or negative in an interval. Pos or neg on interval. So again, I'm talking about f prime. What can f prime tell me? It talks about the increasing, decreasing nature of a function based on the fact that if f prime is positive or negative on an interval. If it's positive, it's increasing. If it's negative, it's decreasing. F prime also talks about concavity based of f of x based on if on that interval, if f prime on interval is not positive or negative, I'm talking about it, is it increasing or decreasing?
I thought it was double prime.
We're getting there.
Double prime.
We're not going to talk. We introduced double prime. We understand second derivative talks about the concavity on those intervals. But now let me summarize. I'm trying to back up and summarize what we've done. I'm only talking about first derivative. The first derivative can tell you information about the increasing, decreasing. And by the way, yes, second derivative talks about concavity, but first derivative can kind of clue you in on concavity. Remember, we're talking about not only where the first derivative is positive and negative, here, right here, but we're also identifying if the first derivative is increasing or decreasing. Okay, that's why I'm talking about increasing or decreasing.
But that's always true, or
Always true.
But okay, so we do second derivative just to check.
To check and also to, it's more information. The second derivative helps you find the points of inflection.
Okay.
Okay,
So
we can't really find
where
this.
It's doing the concavity.
Yes, on the intervals. The first derivative can give you information. It gives us information that, hey, if it's positive or negative, it's increasing, decreasing. Okay? But if first derivative is increasing, then the graph is concave up. Okay? We're going to see more of this. All right, let's talk about second derivative now. Hold on, hold your questions because I'm trying to just lay this out succinctly. Second derivative tells us strictly concavity. Well, not strictly because I'm going to show you something else that's going to be kind of annoying. All right, concavity of f of x based on, wait a minute, f double prime being positive or negative. Okay, so on an interval, if second derivative is positive on some interval, then it's concave up. On the same on another interval, if second derivative is negative, it's concave down. Positive is up. Negative is down. Now, I'm going to stop there before I introduce more information here. I'm going to kind of clear questions and stuff.
So again, like if you draw, like, just go a little bit down there.
Yep.
If you say, okay, let's say you want us to x squared, right?
X
So,
squared.
X squared. The first derivative
There's-
is 2x, right?
First derivative is 2x.
The
That is
second-
that.
The second derivative is just 2.
Right, which is that.
Exactly. So the second derivative tells us the point of inflection, right?
When you solve it, yeah, but in this case, this has no point of inflection. It's concave up. What is a point of inflection? Where it changes concavity. Is there a change in concavity on my U?
Oh,
No.
just that, okay.
So let's look at this. This is a very simple example. Notice that this is my y prime, this is y, and this is y double prime. Notice y prime is increasing everywhere. What does that tell you about concavity?
Just increase.
It's concave up. When y prime is increasing, okay, y is, I bet you I can make a nice little chart here. Concave up. When y prime is decreasing, y is concave. I don't write very well with this thing. Now, that's first derivative telling me that information. Second derivative, notice second derivative is positive everywhere. Therefore, it's concave up everywhere. Okay, you can find out concavity two ways. First derivative, based off if it's increasing or decreasing, or second derivative if it's positive or negative. All right, let's see if I can write that out. Concavity. It's where f prime is increasing or decreasing, or f double prime is positive or negative. Let's meditate on that. All right. Concavity. It's where f prime is increasing, decreasing, but it's where f double prime is positive or negative. Yeah. Yes. Here's some right here.
And or.
Or,
All right.
um,
And or. I mean, both situations are happening. Okay. Second derivative is positive, and first derivative is increasing everywhere.
this may be a stupid question,
Yeah.
but how do you know that that y del prime is positive and just the one?
You're going to test values.
Oh.
That's why I made you do this little chart real quick. These are my test values between -2 and 2, basically. So this is everything left of -2. This is everything in between -2 and 2. This is everything to the right of 2. You pick some values in that interval. -3 is less than -2. When I test it, notice that I get f double prime is positive. Therefore, it's up. Okay? So, concavity, it's where f prime is increasing or decreasing, or f double prime is positive or negative. Now, guess what? Let's talk about increasing, decreasing. There's one more little rule, and then we can kind of breathe here. Yeah.
Can you go back up to the chart?
Yes. That thing?
So, yeah, like for the -3, why is it up? Is it based on positive or negative?
It's based off positive or negative.
But if
This
it's negative.
No. X is -3, but when I put it into second derivative, I get a positive answer. I'm saying f double prime of -3,
okay,
I get some positive number. We're gonna do one all the way. I'm gonna pick a very hard one, and we're gonna hack it all the way through to the end. And I'll get the calculator out, and we'll look at values, and we'll chart it out. Okay? So this is saying f double prime is negative when I evaluate it at 0. Therefore, it's down. And then when I plug 3 into second derivative, I get a positive. Therefore, it's up. Okay. Guys, there's one more little rule I got to talk about. And that's the increasing, decreasing. How did we find our extreme as max and mins? Remember what we would do? We would take a point, and we would plug it into first derivative, then plug it into second derivative. Guess what? There's a second derivative test for max and min. Yeah, okay? So here's how this works. Let's say I have -1 and 1. I don't know what these functions are. I'm just using fictitious functions here. Here's the rule, guys. This is kind of cool. Remember, we'd have to plug in a value to the left and to the right. And we'd have to see if there's a sign change. Second derivative rule says this. Don't plug in the value. Plug the actual number in. Into, all right, the derivative here. If it's positive, it's a min. This is the only thing that's opposite of common sense. Your common sense would think if it's positive, it's max, negative min, okay? F double prime of some v, if it's negative, it's a max. That's it, guys. We're done. All right. That is all the curve sketching, max, mins, points of inflection, concavity. Now we need to put it together. We need to do lots of problems together. Okay.
Second derivative test.
It's life. It kind of sweetens the game a little bit because now you don't have to plug in two values. You can just plug in one
So
value.
you're trying to find like the rating stuff and figure out what's
Yep.
actually.
So
Absolutely.
you plug in the critical point.
This is a critical point found from f prime.
Yeah, so instead of having a big 2.
Exactly. You
plug
plug that into the second derivative.
Okay.
If you get a positive answer, it's a min. Okay? All right, guys, we're going to take a one all the way through here. Let me find a good one here. All right. Here's going to be our function. Y equals x to the fourth minus 4x cubed. All right? We're going to take this one and find stuff. Actually, let's do a better one than that. Let's find a really cuckoo one. Y equals negative 3x to the fifth plus 5x cubed. All right, so for those of you who are very step-oriented, let's just get it out of the way. Let's find our first and second derivative.
We can do like 4 derivatives, right? But
You can go forever, yeah, but some of them don't have any meaning. Second derivative has meaning. Third derivative has some meaning, but not for us in calc. We do not find third derivative in this course. Okay, it doesn't have any meaning for us. All right, everyone okay? Did I do my derivatives right? Yep, okay. All right, first step is find all the derivatives. Second step, set all of them equal to 0. Let's just get that out of the way. Okay, when I do this one, I'm going to factor out a negative 15x squared, and I'm left with x squared minus 1. So I get x equals 0, comma 1, comma negative 1. There's my list of critical points from first derivative. Is it undefined anywhere? I'm just going to keep doing this as a reminder. Okay? No. Good. But I'm going to keep saying it every time we do it. Is it undefined? Is it undefined? Because students always forget that. They forget to analyze and see, oh, wait a minute, is it undefined somewhere? Okay? Because things can happen at those values as well. All right, when we take second derivative, set it equal to 0, I'm going to factor out a 30x. And I'm left with negative 2x squared plus 1. So I get x equals 0. And square root plus or minus square root of 1/2. I'll list it out separate. Okay. More critical points. Okay, so let's pause. First derivative equals to 0, found a bunch of points. Second derivative equals to 0, found a bunch of points. Okay. The critical points from first derivative have to deal with extremas. The critical points from the second derivative are, I call them papoys, possible points of inflection. Okay, these are papoys, and these are possible extremas. All right, pexes. Here we go. Sorry. All right, let's pause there. Let's see what we're okay. Set it, we differentiate everything, set it all equal to 0, and we found a bunch of values. All right, here we go. Let's start talking. Now I want to use my new second derivative test for max and min. Now, oh, by the way, hey, 0 appears in both. Guys, it won't be both. It can't be a max and min or an extrema and a point of inflection. I don't think physically you can draw that. Okay? So
what would it be?
It's one or the other. All right, so you're going to have to test it. All right, here we go. Our new rule that we just learned, we're going to find out if these are maxes and mins, says this. If I plug it into second derivative, let's see what our answers are. If I plug 0 into second derivative, I get 0, don't I? It's not positive or negative, so 0 is not an extrema. In fact, you'll find the pattern that if the number appears in second derivative as a 0, it will not be an extrema. It can't be both.
So it can't be an extrema if it equals 0?
No, it can't be an extrema if that same 0, that same solution, is also a solution to the second derivative. Okay? All right, so now we're testing 1 and negative 1. I'm going to plug 1 into the second derivative. I'm doing f. I should be using f. F double prime of 1. Let's see what we get. I get negative 60 plus 30. So the point is, it's positive or negative? Negative, okay? So, remember our rule. If f double prime at a point, if it's negative, it's a... I'm talking about max or min. Is it a max? It's a max. Okay? We're not talking about concavity yet. We're strictly testing the first possible extremas here. The pexes. All right? That's the only thing opposite of common sense. Our brain wants to associate positive with max and negative with min. I don't know why it does that. Maybe I'm weird. But anyway, it's negative. If f double prime is negative, it's a max. Okay? So 1, I have a max at x equals 1. Abby.
Why are we plugging it into the second derivative?
That's our new rule. We just learned this new cool rule. We don't have to do intervals anymore. All right, let's, for old sake, for fun, let's put in 1 here. And let's test just to the left and just to the right real quick. Okay? Here, let's do a calculator here.
Wait, the new rule is that if we plug in the points, the p x,
What?
the x, the points, the one and
Possible extremas, yep.
possible extremas.
Yep.
If we plug them in the second derivative.
Right.
That's it.
Instead of, right, and we're done.
Negative, they're max. You don't have positive, then
Bam. Okay?
it's easy.
Yep. We don't have to do intervals, but I'm just going to do, we know it's a max, so what should it be, guys? If it's a max, I should be what? Positive, negative, right? Increasing, decreasing. Well, let me, and we do that the first derivative. Let me plug in that real quick. Y equals, all right, so notice I've got this in from second period. Notice y2 is my first derivative. All right, let me go over here, and let me just clear out all these values here. Let me go all the way up. All right, delete, 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 delete. Okay, remember, y2 is my first derivative. It's y1 is my first original function. All right, I'm going to pick a number just to the left of 1. I'm going to do 0.9. I get a positive, don't I? See y2 is what I'm looking at right here. So that's my positive. Now let's pick a value just to the right of 1, 1.1. I get a negative. Okay? So we knew that, but we don't have to test intervals anymore. We can just plug in directly into the second derivative. Hang in there. All right? Okay. Now, let's do negative 1. Let's find out if negative 1, what it is. All right, so f double prime of negative 1, all right, that's going to be a positive 60. And then minus 30. I get a positive. So it's a min. So we have a min occurring at x equals negative 1. All right, so we got my maxes and mins out of the way, guys. We found all those. Now, let's find our pois, or our points of inflection. Here, though, you do have to test intervals. Okay? All right. So here I've got square root of negative square root of 1/2. And here I've got square root of positive 1/2. And now what I do is I test the intervals into second derivative.
What about 0?
We can do 0 real quick. Let's get that out of the way. I look at second derivative for that. If I plug in 0, what do I get?
0.
All right, that's why I got that. So I can't use that.
This is now we're looking for concavity.
Right. So I'm going to pick a value. Be careful. All right. So let's see, actually. So we have to pick, we have 3 points of inflection. Sorry.
But you just got close to it.
All right. So let's pick some values here. All right. Now, I've already got my derivatives and everything in the calculator. So let's plug in, well, square root of 1/2 is what, like 0.7? Is that the bell?
Yeah.
Holy cow. All right, so let's do 0.1.
We're not going to test to the left of it.
Well, I'm point 1 is right here somewhere. So I'm doing this one. This is point 1. I mean, not negative. Point 1. All right, and so we go over to the third column. Look, I get positive here. Now I'm going to pick a value, that means hold water. I'm concave up. And then let's pick a value just to the left of 0. Yep. This thing is slow. All right, so we're going to do negative 0.1. And let's go over to the third column here. I'm negative.
No way. Oh, yeah.
So now I'm down. All right, and then let's pick 2. We can pick up some easy numbers here. Oh, this thing is
Probably gonna be
sluggish.
Up and
2.
down.
And let me go ahead and get it negative 2 in at the same time. All right, so let's go over to here. My 2 yields a negative, and my negative 2 yields a positive. Guys, let's see if we can take all this information right here and piece together what this graph looks like. Are you okay staying?
Sure, it's lunch.
All right. You guys rock. All right, here we go. Let's piece this all together now. All right. So 0, these are points of inflection. They change concavity. So it was negative 1, negative square root of 1/2, positive square root of 1/2, and then positive 1. Everywhere at 1, it's a max. So everywhere, if I had a sign chart, I'm increasing to 1, and I'm concave up. All right?